In this video, we're going to continue our study of Gauss's law. Specifically here, we're going to look at how do we use Gauss's law to solve problems, and what kinds of problems can we solve with Gauss's law. So let's review what Gauss's law says. Remember that ultimately we said Gauss's law is the mathematical expression of the concept that the number of field lines leaving a closed surface is proportional to the amount of charge enclosed. The left-hand side of Gauss's law, the side that represents those field lines crossing the surface, that's what we call electric flux. So the left-hand side is the flux. Remember that the circle on the integral here simply means that we're looking at the flux through a closed surface. So something like a sphere or a cylinder or a box. On the right-hand side, we have the amount of charge enclosed in that surface, and then we also have our new constant epsilon naught. One of the important things to understand about this surface that we're talking about is it's an imaginary surface. We draw it around the charges. It doesn't really exist. So this is one of the things you have to keep in mind, because when we use Gauss's law in a problem, there might be actual physical surfaces in the problem as well. But the surface that we're talking about for Gauss's law is not really there. It's imaginary. It's just something that we draw to help us solve the problem. And you'll see how that works in this video. So let's look at a review question from last time. I said that if you've got a charge Q, I'm just going to make up some different charges here, negative 2Q and 4Q, and I want to know what is the flux through this imaginary surface. So again, I'm just drawing that surface. It's imaginary. The other thing to remember is these are surfaces, so these are three-dimensional. And so when I draw this obviously in 2 dimensions, I'm just drawing a cross section of it. But imagine like, you know, a balloon or a blob of some sort is what my circle here represents. So there's an easy question that Gauss's law allows us to answer, and that is, what is the electric flux coming out of that surface? Remember that since the flux is equal to the charge enclosed divided by epsilon naught, if I want to know how much flux is coming out of that surface, all I have to do is add up the total charge. So here we have 4 minus 2 is 2 plus 1. We get 3Q over epsilon naught. So it turns out finding the flux through a surface is not hard. It's just a matter of adding up the charge enclosed and dividing by epsilon naught. However, that's actually not very useful. Really what we want to know, what we want to be able to solve for, is the electric field. That's what we want to know. So let's look at how we can use Gauss's law to solve for the electric field. Well, the first question in using Gauss's law is, if we want to solve for the electric field, can we really just pick any surface that we want? You'll notice here that I've just been, drawing a surface however I want to. Well, this is the key thing to understand. We can't pick just any surface if we want to be able to solve for the electric field using Gauss's law. Think about why that is. Here's the problem. We want to solve for E, but E is stuck inside an integral. So how do you solve for something that's stuck inside an integral? You can't integrate something you don't know. And so here's the way we actually use Gauss's law. There's kind of a little bit of good news here. We never solve this integral. We never actually have to do the integral when we use Gauss's law. What we do is we have to find a surface over which the electric field is constant. So if the electric field is constant over the surface, then remember our definition of flux simplifies just to the dot product of E and A. But that's only true if E is constant over the surface. Therefore, if we can find a surface over which the electric field is constant, then Gauss's law just becomes EA cosine theta equals the charge enclosed over epsilon naught. And now we're just doing algebra. And algebra is easy, at least compared to calculus. So this is the crux of using Gauss's law, is that you've got to be able to figure out, is there a surface that you can draw over which the electric field is constant, even though you don't know what it is yet? And if you can't find a surface where the electric field is constant, then Gauss's law might be true, but you can't use it to solve the problem. Let's look at some examples. So here I've got a charge Q, and Q is surrounded by two different surfaces. This green spherical surface with Q at the center, and then this blue kind of blob of a surface. So the first question, Q is a positive charge. What is the electric flux through surface number 1? So in other words, through the green surface, what's the flux? Well, hopefully you just said it's Q over epsilon naught, because the charge enclosed is just that one charge Q. So the flux through the surface number 1, easy to find. What's the flux through surface number 2? Well, that's the big blue blob. Notice that again, the amount of charge enclosed in that blue blob is just Q, and so the flux is the same, Q over epsilon naught. The next question, over which surface is the electric field constant? Well, clearly, surface A1. And that's because wherever I am on this green surface, I'm the same distance from that charge. So I know the electric field would be the same at any point on that surface. Clearly, the electric field on the blue surface is not the same at every point because I'm different distances from that charge. So if we wanted to use Gauss's law to find the electric field of this charge, we'd need to pick this surface to do it. We could not use the blue surface. Here's a question for you. What's the electric flux through the green surface? Go ahead, pause the video, and answer the question. Okay, well, we've got this green blob of a surface here, and we can see that it encloses two different charges. It has a charge of plus Q, and it has a charge of minus 2Q. Divide that by epsilon naught. The flux is negative Q over epsilon naught. And so the correct answer is B. So again, whenever you're asked a question about electric flux, that's the easy question, because it's literally add up how much charge there is enclosed and divide by epsilon naught. The hard question is, what is the electric field at some point? So now, think carefully about this question. Choose the correct statement. Gauss's law cannot be used to solve for the electric field in this problem, or Gauss's law can be used to solve for the electric field in this problem. Go ahead, pause the video, think about it, and then restart the video. The correct answer is A. Gauss's law cannot be used to solve for this problem. Here's the issue. Remember, to be able to solve for Gauss's law, we've got to be able to have to be able to get rid of this integral. The only way we can get rid of that integral is if the electric field is constant over the area of the surface we picked. Notice the electric field is not at all constant over this surface. In fact, here the electric field is going in, but over here it's coming out. So the electric field is not at all uniform over that surface. Therefore, we can't get rid of the integral. And you can't integrate something you don't know. So we can't use Gauss's law to solve that problem. Now, by the way, again, we know how to solve this problem just using the electric field of a point charge, but we can't use Gauss's law to do it. So as I mentioned in the previous video, Gauss's law, although it's always true, can only be used to solve for the electric field in very symmetrical situations. Spherically symmetrical, or if we have cylinders, or if we have planes, all of those are situations where we can solve for the electric field using Gauss's law. Because Gauss's law is difficult, what I found in years of teaching is the first time you see it in this course, it's best to just concentrate on one symmetry. And so you'll notice that every problem we do is going to involve spherical symmetry. So let's do an example that we can do with Gauss's law. The question is, find the electric field due to a positive point charge. Now remember, we already know the answer. The electric field of a point charge is kq over r squared for a positive charge. How would we use Gauss's law to do this? So the first and most important step in solving Gauss's law is this. Pick a surface so that the electric field is constant over the surface. If you can't find a surface over which the electric field is constant, you can't use Gauss's law. So here's the charge q that I'm trying to find the electric field of. In other words, I want to know what is the electric field at some distance r from that charge. Well, I've got to draw a surface that goes through the point where I want to know the electric field, and that I can argue the electric field is the same everywhere on that surface. Well, as long as I'm the same distance r away from the charge, no matter where I am on that surface, the magnitude of the electric field should be the same. So that surface meets the requirement. Now, the next thing I've got to do is I've got to think a little bit about the dot product. So in other words, I've figured out a surface over which the electric field is constant. So I go from here down to E dot A, and is equal to the charge enclosed over epsilon naught. And actually, you know, let me just work out what the charge is. The charge enclosed in my surface is just q. So I'll just put in q over epsilon naught. And I'm going to rewrite the dot product as EA cosine theta. And so we've got to figure out what the magnitude of A is. Well, remember, this is a spherical surface, so A is just 4 pi r squared. So I can replace the area with 4 pi r squared. Now, what do I put in for the angle theta? Remember, theta is the angle between the surface area vector and the electric field. Because it's a positive charge here, I know that the electric field goes away, so E is straight out, no matter where I draw it. Notice that the surface area vector of a closed surface is always out, no matter where I am on the surface. So that's A. And therefore, I can see that the angle between E and A is 0. So theta is 0 degrees. So cosine of 0 equals q over epsilon naught. Or E is equal to 1 over 4 pi epsilon naught q over r squared. Remember that 1 over 4 pi epsilon naught is just the definition of our other constant k. So since k is 1 over 4 pi epsilon naught, the electric field of my point charge is kq over r squared. And that's good because, of course, we knew that was the answer from previous material we've covered. But that's how we use Gauss's law to solve a problem. I want to just go back one slide, a couple slides here actually, to emphasize something. I want to go back here and I'm going to put a bunch of stars on this slide, because this is the key slide to understand. We've got to be able to find a surface over which the electric field is constant. If there isn't one, we can't use Gauss's law to solve the problem. If there is, then we can simplify by changing the integral of E dot dA to just E dot A. And you'll notice that's what we did in that problem. Let's take a look at the following question. Imagine the electric field inside a charged metal spherical shell. What is the direction of the electric field at point P? So I want to think about this with you conceptually just a little bit, and then I'm going to pause the video and let you think about it. Or I want you to pause it and think about it. You'll notice that at point P, this charge on the sphere, and again, this is a spherical shell, so it's empty in the middle. We've got a shell that has a uniform positive charge spread on it. The electric field at point B due to that little bit of charge would be in that direction. The electric field due to that amount of charge would be here, here, etc. So you'll notice that any charge to the left of this line is contributing to an electric field pointing to the right. On the other hand, any charge over here is creating an electric field to the left. However, those electric fields are going to be smaller because we're farther away from that charge. And so the question is, which is it going to be? Is the electric field going to be to the right, to the left? Is there no electric field? Go ahead, pause the video and think about it. So the answer is D. There is no electric field at point P. Now this is kind of a cool problem to do with Gauss's law. Remember that to use Gauss's law, we have to be able to figure out a surface over which we can make the argument that the electric field is constant, even though we don't know what the electric field is yet. And we need the surface to go through the point where we want to know the electric field. So here's the Gaussian surface I'm going to draw. It's a sphere that's centered inside our physical sphere of charge. So if you look at that surface that I've drawn, we can easily make the argument that the electric field is constant over that surface because we're equidistant from the positive charge. So no matter where we are on that dotted line, there's no reason the magnitude of the electric field should be different than any other place on that line. That's the requirement for using Gauss's law. So we know E is constant over that spherical surface that I'm representing by the red dots. So I can start with Gauss's law in its full form. The integral of E dot dA is equal to the charge enclosed divided by epsilon naught. And I can immediately simplify that to EA cosine theta. Since we've successfully found where we found a surface that we can make the argument the electric field is constant. Now, I don't know actually what the direction of the electric field is at this point, but it's either just from symmetry got to be in or out. So you'll notice that whether it's out or whether it's in doesn't really matter too much because theta is either 0 or 180. Okay? So let's just assume that it's 0. That gives me EA is equal to Q over epsilon naught, and of course E is 4 pi r squared, where r is the distance from the center to where I want to know the electric field. But how much charge is enclosed in my dotted line? Notice there's none. Q enclosed is 0. So that's 0. Well, r is not 0 and 4 pi is not 0. So the only way this could be true is the electric field has to be 0. So think about that. The electric field has to be 0 anywhere inside that shell. Even if you're right up to the surface, right at that point, or if you're here, or here, or here, or here, the electric field everywhere inside there has to be 0, because I can move that Gaussian surface anywhere I want inside there. So that's the power of Gauss's law, that we don't have to do any complicated math to figure out that the electric field at that point, or any point inside that shell of charge, is equal to 0. Let's look at a slightly more complicated problem. It says 2 conducting spherical shells have charges shown in the diagram. What's the electric field in these 3 ranges? So in other words, I want to know what is the electric field anywhere in here, then what's the electric field between the shells, and what's the electric field outside the shells. So let's start with what is the electric field at any point r less than r1? So in other words, what is the electric field at some point right here? Well, you might recognize that this is really the same problem we just did. In other words, because my shells are spherically symmetrical, so they're lined up with this point, the center of both of the shells, and therefore, if I say, what's the electric field at this point, I can draw a spherical surface in here. That's my imaginary Gaussian surface. And I can make the argument that there's no reason the electric field shouldn't be the same in magnitude everywhere on that surface, because every point on that dotted line is equidistant from those two physical shells. Well, therefore, I can go from E dot dA is equal to the charge enclosed over epsilon naught, and I can go right to EA cosine theta is equal to the charge enclosed. But what's the charge enclosed in that dotted line? There is no charge, 0. And therefore, the electric field anywhere at a radius less than r1 has to be equal to 0. So there's no electric field anywhere inside that first physical shell. Now let's look at what is the electric field at some point in between the two shells. So what is the electric field right here at this point? Once again, I draw a Gaussian surface, and because that surface is equidistant from both of the shells, I can make the argument that the electric field has to be the same everywhere on that dotted surface. Now, I know Q1 is positive, so I can guess that the electric field is straight out at that point. We know that the surface area vector of my imaginary surface is always out. So I know that theta is equal to 0. And so now I just start working through Gauss's law. Again, because I found a surface that the electric field is constant over, I'm just going to jump right to EA cosine theta is charge enclosed over epsilon naught. Well, the charge enclosed is just the charge on this inner physical surface, which is Q1. So I'll do Q1 over epsilon naught. And I know the electric field is what I'm trying to find. The surface area is the surface of my Gaussian surface. That's 4 pi r squared times the cosine of 0. And what I get is that E is 1 over 4 pi epsilon naught Q1 over r squared, or K Q1 over r squared. Now that's an important result because hopefully you recognize what that looks like. I'm just going to make a note. Same as E of a point charge. So there are a couple important things to notice here. Once you are outside a shell of charge, so in other words, we're outside this shell, you can't tell the difference between the electric field created by that shell and the electric field that would have been created if all of that charge Q1 had simply been located right there. The electric field is the same. By the way, you're already familiar with this concept from gravity. Remember, the force of gravity created by the Earth, we always treat it in first semester physics as if it's just all located right at the center. Once you're outside the surface of the Earth, it acts as if all the mass is right at the center. So the same idea here. The other thing you'll notice is the fact that there's charge out here does not affect the electric field anywhere in between the shells. So that makes sense because remember in the previous example we looked at what's the electric field inside the first shell and we said it was 0. So the electric field contributed by this outer shell is 0 inside it. And so the only thing that matters is the electric field created by this shell. As our final example in this video, let's finish the problem by looking at what is the electric field at some distance r where we're now outside both shells. So what is the electric field right here at this point? Notice that because Q2 is negative, we might guess that the electric field at this point is going to be in. And so I'll just put that as our direction for E. We know that the surface area vector is out. And we know we have to create a Gaussian surface where we can make the argument that the electric field is the same everywhere on it. And that's going to be by just creating a shell that looks like that. Okay, so everywhere on that shell, the electric field should be the same because we're equidistant from the two physical shells in the problem. That means I can jump right to EA cosine theta is equal to the charge enclosed over epsilon naught. And now I'm going to put in what I know. So the area is 4 pi r squared, where r is this distance from the center. I've got the cosine of 180, so that's just going to give me a -1. But how much charge is enclosed in my dotted line, in my Gaussian surface? Well, it's Q1 plus Q2 over epsilon naught. So I've got -E 4 pi r squared is equal to Q1 plus Q2 over epsilon naught. However, in this problem, Q1 and Q2 are related in this way. So you'll notice that there is no net charge inside that surface. And so even though I've got E 4 pi r squared on the right, since it's equal to 0, the electric field has to be 0 anywhere outside that second sphere. So whether I'm right here, or out here, or here, the electric field at all of those points is equal to 0. So that's how we use Gauss's law. We've got to pick a surface where we can make the argument that the electric field is constant. As long as we can do that, then the flux just simplifies to EA cosine theta, and then we can solve algebraically for the electric field. In our next video, we'll continue to look at examples and the ramifications of Gauss's law.